Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young. Section 47, Pencils and Ranges of Conics. Order of Contact. The theorems of the last section and their plane duals determine the properties of certain systems of conics, which we now proceed to discuss briefly. Definition. The set of all conics through the vertices of a complete quadrangle is called a pencil of conics of type 1. Figure 61. Definition. The set of all conics tangent to the sides of a complete quadrilateral is called a range of conics of type 1. Figure 62. Theorem 19 and its plane dual give at once. Theorem 22. Any line not through a vertex of the determining quadrangle is met by the conics of a pencil of type 1 in pairs of an involution. Theorem 22 prime. The tangents through any point not on a side of the determining quadrilateral to the conics of a range of type 1 are pairs of an involution. Corollary. Through a general point in the plane there is one and only one, and tangent to a general line there are two or no conics of a given pencil of type 1. Corollary. Tangent to a general line in the plane there is one and only one, and through a general point there are two or no conics of a given range of type 1. Footnote. This form of Desargues' theorem is due to Charles Theorem, Annales de Mathématiques, Volume 17, 1826, page 180. Footnote. The vertices of the quadrangle are regarded as exceptional points. Definition. The set of all conics through the vertices of a triangle and tangent to a fixed line through one vertex is called a pencil of conics of type 2. Figure 63. Definition. The set of all conics tangent to the sides of a triangle and passing through a fixed point on one side is called a range of conics of type 2. Figure 64. Theorem 20 and its plane dual then give at once. Theorem 23. Any line in the plane of a pencil of conics of type 2 which does not pass through a vertex of the determining triangle is met by the conics of the pencil in pairs of an involution. Theorem 23 prime. The tangents through any point in the plane of a range of conics of type 2 which is not on a side of the determining triangle to the conics of the range are the pairs of an involution. Corollary. Through a general point in the plane there is one and only one conic of a pencil, and tangent to a general line in the plane there are two or no conics of the pencil. Corollary. Tangent to a general line in the plane there is one and only one conic of the range, and through a general point in the plane there are two or no conics of the range. Definition. The set of all conics through two given points and tangent to two given lines through these points respectively is called a pencil or range of conics of type 4. Figure 65. Theorem 21 now gives at once. Theorem 24. Any line in the plane of a pencil of conics of type 4 which does not pass through either of the points common to all the conics of the pencil is met by the conics of the pencil in pairs of an involution. Through any point in the plane, not on either of the lines that are tangent to all the conics of the pencil, the tangents to the conics of the pencil are the pairs of an involution. The line joining the 2 points in common to all the conics of the pencil meets any line in a double point of the involution determined on that line, and the point of intersection of the common tangents is joined to any point by a double line of the involution determined at that point. Corollary. Through any general point or tangent to any general line in the plane, there is one and only one conic of the pencil. Footnote. The classification of pencils and ranges of conics into types corresponds to the classes of the corresponding plane collineations, chiefly exercises 2, 4, 7 below. Footnote. The remainder of this section may be omitted on the first reading. The pencils and ranges of conics thus far considered have in common the properties: 1. That the pencil, or range, is completely defined as soon as two conics of the pencil, or range, are given. 2. The conics of the pencil, or range, determine an involution on any line, or point, in the plane with the exception of the lines, or points, on the determining points, or lines, of the pencil, or range. 3 other systems of conics may be defined which likewise have these properties. These new systems may be regarded as degenerate cases of the pencils and ranges already defined. Their existence is established by the theorems given below, which, together with their corollaries, may be regarded as degenerate cases of the theorem of Desargues. We shall need the following. Lemma. Any conic is transformed by a projective collineation in the plane of the conic into a conic such that the tangents at homologous points are homologous. Proof. This follows almost directly from the definition of a conic. Two projective flat pencils are transformed by a projective collineation into two projective flat pencils. The intersection of pairs of homologous lines of one pencil are therefore transformed into the intersections of the corresponding pairs of homologous lines of the transformed pencils. If any line meets the first conic in a point P, the transformed line will meet the transformed conic in the point homologous with P. Therefore, a tangent at a point of the first conic must be transformed into the tangent at the corresponding point of the second conic. Theorem 25. If a line P0 is tangent to a conic A squared at a point P0, and Q is any point of A squared, then through any point on the plane of A squared, but not on A squared or P0, there is one and only one conic B squared through P0 and Q tangent to P0 and such that there is no point of P0 except P0 having the same polar with regard to both A squared and B squared. Proof. If P' is any point on the line not through P0 or A squared, let P be the second point in which P0P' meets A squared. Figure 66. There is one and only one elation with center P0 and axis P0Q changing P into P'. Theorem 9 of Chapter 3. This elation, by the lemma above, changes A squared into another conic B squared through the points P0 and Q and tangent to P0. The lines through P0 are unchanged by the elation, whereas their poles on P0 are subjected to a parabolic projectivity. Hence, no point on P0 distinct from P0 has the same polar with regard to A squared as with regard to B squared. Since A squared is transformed into B squared by an elation, the two conics can have no other point in common than P0 and Q. That there is only one conic B squared through P', satisfying the conditions of the theorem, is to be seen as follows. Let QP meet P0 in S, and QP' meet P0 in S'. Figure 66. The point S has the same polar with regard to A squared as S' with regard to any conic B squared. Since this polar must be the harmonic conjugate of P0 with regard to P0Q and P0P. Let P be the tangent to A squared at P, and P' be the tangent to B squared at P', and let P and P' meet P0 in T and T' respectively. The points T and T' have the same polar, namely P0P with regard to A squared and any conic B squared. By the conditions of the theorem and the projectivity, P0ST is projective with P0S'T' must be parabolic. Hence, by Theorem 23, Corollary, Chapter 4, the quadrangular set Q of P0ST, P0T'S', hence P and P' must meet on P0Q in a point R so as to form a quadrangle, RQP'. This determines the elements P0Q P', P0P' of B squared, and hence there is only one possible conic B squared. Corollary 1. The conics A squared and B squared can have no other points in common than P0 and Q. Corollary 2. Any line L not on P0 or Q, which meets A squared and B squared, meets them in pairs of an involution in which the points of intersection of L with P0Q and P0 are conjugate. Proof. Let L meet A squared in N and N1, B squared in L and L1, P0Q in M and P0 in M1. Figure 67. Let K and K1 be the points of A squared which are transformed by the elation into L and L1 respectively. By the definition of an elation, K and K1 are collinear with M. While K is on the line LP0, and K1 on L1 P0. Let K N1 meet P0 in R, and N P0 meet K K1 in S. Then, since N, K, N1, K1 are on the conic to which P0 is tangent at P0, we have, by Theorem 6, applied to the degenerate hexagon P0, P0, K1, K, N1, N, that S, L1, and R are collinear. Hence, the complete quadrilateral SR, KN1, KK1, L has pairs of opposite vertices on P0M and P0M1, P0N and P0N1, P0L and P0L1. Hence, the quadrangular set Q of MNL, M1N1L1. Footnote: this argument has implicitly proved that three pairs of points on a conic, as KK1 and N1 P0Q, such that the lines joining them meet in a point M, are projected from any point of the conic by the quadrangular set of lines. Theorem 16, Chapter 8. Definition: the set of all conics through a point Q and tangent to a line P0 at a point P0, and such that no points of P0 except P0 has the same polar with regard to two conics of the set, is called a pencil of conics of type 3. Figure 68. Definition: the set of all conics tangent to a line Q and tangent to a line P0 at a point P0, and such that no line on P except P0 has the same pole with regard to two conics of the set, is called a range of conics of type 3. Figure 69. Two conics of such a pencil or range are said to have contact of the second order, or to osculate at P0. Corollary 2 of Theorem 25 now gives at once. Theorem 26. Any line in the plane of a pencil of conics of type 3, which is not on either of the common points of the pencil, is met by the conics of the pencil in the pairs of an involution. Through any point in the plane, except the common points, there is one and only one conic of the pencil, and tangent to any line not through either of the common points, there are two or no conics of the pencil. Theorem 26 prime. Through any point in the plane of a range of conics of type 3, which is not on either of the common tangents of the range, the tangents to the conic of the pencil are the pairs of an involution. Tangent to any line in the plane, except the common tangents, there is one and only one conic of the range. And through any point not on either of the common tangents, there are two or no conics of the range. The pencil is determined by the two common points, the common tangent and one conic of the pencil. The range is determined by two common tangents, the common point and one conic of the range. Theorem 27. If a line P0 is tangent to a conic A squared at a point P0, there is one and only one conic tangent to P0 at P0 and passing through any other point P' of the plane of A squared not on P0 or A squared, which determines for every point of P0 the same polar line as does A squared. Proof: let P be the second point in which P0 P' meets A squared. Figure 70. There is one and only one elation of which P0 is center and P0 axis, changing P into P'. This elation changes A squared into a conic B squared through P', and is such that if Q is any tangent to A squared at a point Q, then Q is transformed to a tangent Q' of B squared passing through Q P0, and Q is transformed into the point of contact Q' of Q', collinear with Q and P0. Hence, there is one conic of the required type through P'. That there is only one is evident because if L is any line through P', any conic P squared must pass through the fourth harmonic of P' with regard to L P0, and the polar of L P0 as to A squared. Theorem 13. By considering two lines L, we thus determine enough points to fix B squared. Corollary 1. By duality, there is one and only one conic B squared tangent to any line not passing through P0. Corollary 2. Any line L not on P0 which meets A squared and B squared meets them in pairs of an involution, one double point of which is LP0 and the other the point of L conjugate to LP0 with respect to A squared. A dual statement holds for any point L not on P0. Corollary 3. The conics A squared and B squared can have no other point in common than P0 and no other tangent in common than P0. Proof. If they had one other point P in common, they would have in common the conjugate of P in the involution determined on any line through P according to Corollary 2. Definition. The set of all conics tangent to a given line P0 at a given point P0 and such that each point on P0 has the same polar with regard to all conics of the set is called a pencil or range of conics of type 5. Two conics of such a pencil are said to have contact of the third order or to hyperosculate at P0. Theorem 27 and its first two corollaries now give at once. Theorem 28. Any line L not on the common point of a pencil of type 5 is met by the conics of the pencil in pairs of an involution, one double point of which is the intersection of L with the common tangent. Through any point L not on the common tangent, the pairs of tangents to the conic of the pencil form an involution, one double line of which is the line joining L to the common point. There is one conic of the set through each point of the plane not on the common tangent, and one conic tangent to each line not on the common point. The pencil or range is determined by the common point, the common tangent, and one conic of the set. Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renhold, with programming and illustration by Jim Renhold, 2019. Thank you for listening.